Okay. So I hope everybody can see that. My name's John Crawford. I'm the Professor of Strategy and Technology at the Adam Smith Business School in the University of Glasgow. But I'm also a theoretical physicist who's been working on trying to understand soil and how it works for about 30 years. We know that agriculture is degrading our soil. It's a very recent UN article being published on this, on the left of the slide there. We're diverting almost a third of net primary productivity to grow our food and fiber, and bioenergy. And in doing that, we've degraded 25% of the world's ice-free land. And it's been estimated that by 2050, human activity will have had a negative impact on up to 90% of the land surface. And the problem with that is that land degradation is both exacerbating and being exacerbated by climate change. And the reason for that is because soil contains more carbon than the atmosphere and all of the plants on Earth combined. And so when land is degraded, it releases more carbon into the atmosphere, accelerating climate change, and then extremes of climate contribute to land degradation through drought and fire, for example. So what I want to talk about in this short presentation is, I reckon we've got about 10 years to solve a lot of these problems. So how do we deliver, how do we restore soil health in 10 years globally? I say there are three key barriers to delivering soil health, and then I've listed four. So I'm going to say there's four key barriers. First of all, our understanding of the soil science has significant gaps. Farming practices and incentives are very much focused on producing more crops with less attention and less available resource to support soil health. The other thing is that improving soil requires a lot of effort, and it also takes time. And I'll talk a bit about that later. And there's no such thing as a soil. There is a huge diversity of soils globally, and it certainly isn't a one-size solution fits all soils in all farms around the world. And so we need to tailor solutions to farms. And then the final barrier, which I wasn't going to mention, but decided to mention, is that the global political landscape has become a lot more nationalistic in the last 5 years. And that makes collaborative behavior between governments a lot more difficult. And therefore, coordinated behavior to combat climate change is a lot more difficult as well. So we cannot rely on political leadership. We have to look elsewhere for leadership. So what I'm going to focus on in this presentation is primarily the soil science and some of the things that I've been trying to find out over the years. And then I'll talk very quickly about where we might go to look for leadership that is both scalable and can deliver the impacts we need in the time that we have. Soil health is a very vague concept, and for that matter, regenerative agriculture is a very vague concept, and that causes a lot of difficulty, not just from farmers who want to improve their soil health, but also from the point of view of selling it to consumers so that they might pay more or at least choose products that are from farms that are regenerative or that build healthy soil. And also at political landscape, how do you define policies around things that are quite vague? However, we're not alone, and I will argue that soil, the reason that it's difficult to define these concepts is because soil and agriculture are probably the most complex activities. Well, soil is the most complex material that we interact with, and agriculture is actually, if it's done well, is also very complex. So if we turn to human health, so there's obviously been a huge resource expended on human health over hundreds of years, thousands of years, but certainly most recently. And despite that enormous investment in understanding human health, we don't actually have a very good definition of human health either. And the World Health Organization definition is that health is a state of complete physical, mental, and social well-being. Now, with that definition, none of us are healthy because none of us are in a state of complete well-being. And a definition like that still tends to promote a medicalization of healthcare over preventative health, and preventative health is still some way behind. And kind of responding to that and following a very interesting book published by Kangelham in 1943, The Lancet launched a global review and a global consultation on how to define health. And in the end, they selected the definition, which is the ability to self-manage and adapt to one's environment. So even if you're in a wheelchair, you can still self-manage and you can still adapt. And of course, the wheelchair is one of those adaptations. So it individualizes healthcare. And I'd like to suggest that we individualize soil health as well, using a very similar kind of approach and definition. So I want to show in the next few slides, I want to try and explain how I think that the ability to self-manage and adapt is actually quite a good definition for soil health. And then I want to show how we can use that to understand how to restore soil health. And I'll do that by focusing on some of the functions that are really important in soil. So what does soil do that's amazing? I think when you boil it all down, the most important property that soil delivers is the ability to enable the coexistence of air and water over a very broad range of environmental conditions. Both air and water are required for active life, and soil is a great environment for keeping those very well mixed. Not only does it mix them, it maximizes the area of the interface between air and water, which means that oxygen can get in and dissolve in water and then be used by microbes that do all the biological effort in soil. And I'll show also that the biological effort in soil is actually very important for delivering the physical behavior of soil too. Now, that property, that fundamental property of soil is delivered by pore scale structure that is smaller than the width of a human hair. So when you pick up a piece of soil in your hand and you look at it and you look at the structure and you can see the pores, that pore space is important, but the really critical stuff is pretty much invisible to the human eye. And we've been using special tools, which I'll show you in a minute, to visualize those structures. And what it's told us is that the structures at those scales are highly organized. They're not random. Now here's an example. This is a high resolution X-ray CT image of a 2mm piece of soil. Now we've used some clever tricks to make it look like soil, but the pore space, the structures that you're flying through just now, that's real pore space. The rendering on the walls is just artificial to make it look like a real soil wall, but the actual pore space is how it looks under high resolution CT imaging. So these structures are about the width of a human hair and smaller. And what you'll notice is that we are able to fly through soil at this scale. Now, if soil was a completely random, disorganized thing, you wouldn't be able to fly through it. At this level of porosity, none of the pores would connect, and you couldn't move through it. And of course, if you can't move through it, neither can oxygen, water, or microbes. So that connectivity is a really critical property of soil at these scales. So not only do these structures allow for the mixing of air and water, they're also highly connected. Now, over the years, I've been developing a theory for the organization of soil structure. And we've got this idea, this is another little video that attempts to show how fungi might move through a packing of soil particles in space. Now, the green stuff, the green particles just represent favorable environments. Now, for the sake of the argument here, we could say that these environments are very well connected to this, to the air, and so they've got lots of oxygen, lots of resource, and that allows the microbe to be very active. And then we can simulate how the soil fungus might move and cover the particles in soil over time as it responds to the areas where which are particularly favorable to supporting microbial activity. And what you can see is over time that the fungi are very good at connecting and enmeshing those favorable environments. And they're not covering the less favorable environments in soil. Now, when the fungus enmeshes soil particles, it stabilizes them against disruption. And the disruption can happen in soil when it wets and when it dries. And so the fungus is, in this case, is stabilizing the environments against disruption through wet-dry cycles after it rains and when it's sunny. And we did a little computer simulation, and on the right-hand side, I can show how the structure evolves over time, and particularly how the connected porosity evolves over time if we assume that the microbes stabilize particle environments that support growth. And what you see, if you can see my cursor, is that over time the porosity connects up to some sort of maximum level, but pretty quickly the porosity connects up across the whole soil structure. And these different curves just represent different levels of compaction, and you can see how a more compact soil struggles to recover that connected porosity compared to a less compact soil, which is why compaction, well, if this theory is correct, is why compaction is such a problem in agriculture. So we call this property, this ability of the physics and the biology to organize, self-organization. And there's a growing realization that many living systems are not just self-organizing, but they're critical. And that means that the self-organization and the way that these things interact, they create a state in the system that's perched between organization and chaos. And we call that a critical state. The reason why living systems are probably in that state is because it allows them to reorganize quickly when the environment changes. And so criticality, this self-organized critical state, gives living systems the ability to adapt whilst maintaining organization. And you can sort of see the analogy here with the definition of health as the ability to adapt and self-manage. So do we have evidence for criticality in soil? Well, here's an example on the right-hand side, a little animation of a two-dimensional slice of soil, if you like. The colors represent connected pore space of different sizes. And what you'll see as the porosity gets close to 50%, suddenly the system connects across the yellow pores, connect across the whole structure, and it very quickly becomes a highly connected pore space. And that's characterized by this power law behavior where we've got connected porosity versus porosity, and you get this abrupt change with porosity, and it's a power law, which means it's not all that means it's not proportional. Now, if we look at soil and using these CT images, we can plot the connected porosity against porosity. And we've done this with the Broadbach experiments, the oldest scientific experiment in the world at Rothamsted in Hertfordshire. 270 years of continuous wheat under a range of different nutrient management regimes. And if we plot the connected porosity versus the porosity for all of those, for soil samples taken from those different treatments, we get this power law behavior. This blue line is a one-to-one line, so that you get to a point round about 25% porosity where the whole pore space becomes highly connected. And I'll explain, yeah. So what we find is when these different treatments, which are different organic or inorganic treatments, have different consequences for the flow of carbon into the system. And what we find is the higher carbon systems are up here. So there's farmyard manure and the wilderness, which is just a field that's been left back to nature for 200, it's not 270 years, it's 170 years, for 170 years. And so that a field that's been farmed with continuous wheat, if the organic matter inputs are high enough, it looks just as good as a back to nature soil. Here's another experiment. This is Highfield, where there's been different treatments over 70 years, grass, arable, and bare fallow. The bare fallow is just soil that's had nothing grown in it, no addition of nutrients, no plants. And you see again, you've got this power law critical behavior, and the grassland has much higher carbon, is up here. So most of the pore space is connected up here. The arable starts to become closer to the critical point down here. And then the bare fallow is definitely nearest to the critical point where the pore space has almost collapsed completely. However, the power law is the same power law as we saw in Broadbach. Now, here's an interesting thing. In 2008, part of the Highfield experiment was the bare fallow treatment was converted back into grassland and arable. And that allowed us to follow the behavior of the different treatments over time, starting from a very degraded soil, to see how quickly the self-organized critical behavior returns. So this is the start. This is again connected porosity up here. This is porosity at these very small scales. And you can see in the bare fallow plot that it's nowhere near any kind of obvious self-organized state. There's lots of, the points are all over the place. But actually after 5 and then 10 years, the points quite quickly collapse onto this critical state. And this is after 70 years, it's the same line. And so you get the idea that the soil under grassland in particular moves most quickly to this self-organized critical or healthy state. This is another way of showing some of this data, only this time this is connected porosity versus the total organic carbon content of soil. And you can see how quickly the connected porosity increases as you increase the soil carbon. And this just highlights the point that even small gains in soil carbon can have significant can lead to significant improvements in the health of the soil in the way that we're measuring it here. Another interesting plot. This time, this is the hydraulic conductivity. So this is using computer simulation to work out how fast water and nutrients can move through these small soil pieces. These small soil structures. And you can see here that for low connected porosity, obviously it doesn't move very well, but as the connected porosity increases, it dramatically changes. Again, it's a power law, and again, it's because of critical behavior, but it shows superimposed, the size of the circles here are the amount of organic carbon in soil. And so you can see the switch, the very rapid increase in the flow rates, even for small changes in carbon in the soil. And then finally, these carbon creates a much more stable soil environment here. This is the proportion of the soil that has no oxygen in it. Now, when you don't have oxygen, you're losing a lot of nutrients through N2O emission. And this is wet conditions, and this is dry conditions. And what you see is the bare fallow. Even for small changes in rainfall or sunshine, you get dramatic changes in the fraction of the soil that has no oxygen in it. And for all environments, you see that it is already a much higher fraction of that soil has no oxygen in it, and so we'll be losing nutrients. Compared with grassland, it's arable in the middle and grassland on the left. So just the final slide. I said I'd come back to where's the leadership going to come from to deliver soil health. So what I'm doing now, and why I've joined a business school, is I'm working with a coalition of leading corporates, global corporates, including the big ag companies and big global oil and gas companies, to develop an investable framework to deliver soil health, to overcome some of the barriers and enable the delivery of soil health by increasing carbon at a global scale and well, hopefully in the next 10 years. We're doing this in cooperation with the World Economic Forum and the UN FAO. And allied to this program, we're establishing a global science advisory group, and the overall ambition is to aim to deliver a gigaton of sequestration by 2030, which would represent about 50% of the carbon offsets required to meet the Paris Agreement. And by bringing together the supply and demand side of the voluntary carbon market, we think we can have an almost order of magnitude saving in the cost, which means that for a given investment, we can improve almost 10 times the area of soil by doing it this way. So in conclusion, carbon provides the energy that soil requires to self-organize and maintain itself in a critical state. In other words, maintain an ability to adapt and self-manage. Carbon is the critical ingredient for that. Increasing carbon inputs stabilizes the state of soil. Ploughing isn't a good thing. Grass is great, but even ploughing, if you've put enough organic carbon in to a system that's been ploughed and continuous wheat for 170 years, you can still make your soil look as good as if you'd left it back to nature. Carbon helps store more water, reduces anaerobic emissions, increases flow from soil into plant roots. And what we've shown in these slides is that management at the field scale impacts on soil at scales of a hair's breadth, which I think is pretty cool. Thank you.